Hi everyone, and welcome to this short video about the binomial theorem. In this video, we will talk about underlying principles like factorials, the binomial coefficient, and the Pascal's triangle. And finally, we will of course, as you may have guessed already from the name of this video, talk about the binomial theorem. You might wonder why this video is being released in this specific week and not earlier. The answer is simply that the binomial theorem is very important and that this week it kind of fitted into our schedule. So don't be confused, it does not explicitly has to do a lot with fields and groups. At the end of this video, we will also prove the binomial theorem together. This proof is not a crucial part to know by heart for the exam, but still it is a good practice and can be very useful, and of course the binomial theorem itself is just very cool, so you might want to check it out. Alright, with that being said, let's start. So the binomial theorem is a super useful formula when you are dealing with a binomial that is potentiated, meaning that we have a binomial to the power of any natural number n. A binomial would be something like x plus y, and you place this inside of the brackets and take it to the power of n. Now, with the help of the binomial theorem, we will be able to nicely rewrite it into a polynomial, which is a sum. This might sound a bit confusing, so let us take a look at the most common example, the first binomial rule. If we consider the binomial a plus b and square this, we will have the first binomial formula. The result is, as you probably already know, a squared plus 2ab plus b squared. This is marked in red here. Let us now look at the next case, i.e. not squaring the binomial anymore, but taking it to the power of 3. If we do this, we can rewrite it as a plus b squared, which resulted in the red term, times a plus b in parentheses. If you multiply this out, you will get a to the power of 3 plus 3a squared b plus 3ab squared plus b to the power of 3. We can also take this further. Let us consider a plus b to the power of 4. Again, we can take the result from the previous calculation and multiply it once more with a plus b. As a result, we will get a to the power of 4 plus 4 times a to the power of 3b plus 6 times a squared b squared plus 4 times a b to the power of 3 plus b to the power of 4. And if we do this once more, so for a plus b to the power of 5, we will get a to the power of 5 plus 5a to the power of 4b plus 10a to the power of 2b to the power of 3 plus 5ab to the power of 4 plus b to the power of 5. And we could continue with this forever. The terms would always get longer and longer. This is quite interesting actually. So if we look at the results, there seems to be some kind of pattern. And this pattern is precisely what the binomial theorem describes, so it gives us the formula and solution for this. Therefore, it is a very powerful and very cool theorem. But before jumping right into the formula, we need to take a step back. So far for the motivation and background of what we are talking about in this video. Let us now take a look at some underlying concepts that we will need for the binomial theorem. You might already know them, but let's recap them anyways. First of all, we need to talk about factorials. You probably have seen them before. They are denoted with the exclamation point sign. So for any natural number n bigger or equal to 1, n exclamation point, which you read out as n factorial, is defined as n times n minus 1 times n minus 2 and so on until you reach the 1. So in other words, you multiply all the natural numbers from 1 to n, and this is then n factorial. To make this clearer, let us shortly take a look at two examples. First of all, we have 3 factorial. With our rule, we can easily calculate it. We start with n, which is 3 in this case, and then always go one natural number downwards and multiply it until we reach the number 1. In practice, this means for 3 factorial that we will multiply the 3 times the 2 times the 1, and then we stop. Therefore, 3 factorial equals 6. For 5 factorial, this works the same. We calculate 5 times 4 times 3 times 2 times 1. The result of 5 factorial is therefore 120. This is pretty much straightforward. Now let us take a look at some important rules concerning factorials. In the definition on the last slide, we had n factorial defined for all natural numbers that are bigger or equal to 1. But what happens to the other numbers? The first 3 rules will give the solution here. First of all, 0 factorial is defined as being 1. There's nothing you can really calculate here, but it is a definition that you should just remember and accept the fact that it has been defined this way. So we know now how to calculate the factorial of the positive natural numbers, which is by multiplying 1, 2, 3 and so on until n. And we also know that 0 factorial is 1. But of course there are also other numbers than these ones. For example, negative numbers. For the negative numbers, as stated in Rule 2, the factorial does not exist. And the same holds for non-integer numbers. As you can see in Rule 3, they also don't have factorials. So now you should be able to know the factorials of any possible number. Let's continue with Rule 4 here. It's not a real rule, but more like a different notation of n factorial. Of course it will yield the same results, the rule is just another notation. Namely the product notation, which you've already learned in week 2. So in product notation, we say that n factorial is equal to the product from I equals 1 to n of I. This means we plug in for I first the starting value, which is 1 here, and then always increase it by 1 until we reach the n. All these terms are multiplied together because they stand in the product sign. This notation is very useful and in general a good example for a product notation that you will encounter quite often. Finally, there's also the 5th rule on this slide. This rule explains how we can take an element, the last element, outside of the factorial. It states that n factorial is equal to n times n minus 1 factorial. When you think about this, it is pretty straightforward because n factorial is the same as n times n minus 1 times n minus 2 and so on. So now, if you have n minus 1 factorial, this is actually almost the same, just that you start at n minus 1 and not at n. The rest is the same. The only number that you do not include here is the n, and therefore n times n minus 1 factorial is the same as n factorial. Let's move on to the binomial coefficient now. For any two numbers n and k, with n bigger or equal to k, and k being bigger or equal to 0, with both n and b being elements of the natural numbers, we call n over k the binomial coefficient. So while we say n over k, they are written inside of parentheses, and on top you have n, and below you have the k. Per definition of the binomial coefficient, n over k is defined as n factorial divided by k factorial times n minus k factorial. Let us take a look at some examples. The first one here is 4 over 2. So using our notation of n over k, n is 4 and k is 2. If we apply the rule of the binomial coefficient now, we can rewrite this to calculate the result. On the top of the fraction, we have n factorial. In our case, this is 4 factorial because n is 4. Below in the fraction, we have k factorial, so 2 factorial in our case, times n minus k factorial, which is 4 minus 2 factorial here, which of course is 2 factorial. Now we can calculate the result easily. 4 factorial is 4 times 3 times 2 times 1, which is 24 in total. 2 factorial is 2 times 2, so 2. This means the fraction can be reformulated as 24 divided by 2 times 2, which is 4, resultingly, and we will end up with 6 as the result of 4 over 2. In the second example, we have 5 over 2. So here, in terms of n over k, n is 5 and k is 2. If we plug this into our formula, we have 5 factorial for n factorial divided by 2 factorial for k factorial times 5 minus 2 factorial for n minus k factorial. This is the same as 5 factorial divided by 2 factorial times 3 factorial, which is 120 divided by 2 times 6, and the result will be 10. The binomial coefficient also has some important rules that you should remember. The first one here is the binomial coefficient for k equals 0. This means that we have n over 0, and independent of the value of n, the result of n over 0 will be 1. And the second rule states that n over n is also 1. Now, if we have n over 1, the result will be n, as you can see in rule 3. And in rule 4, you can see that n over n minus 1 is also n. The last rule here on this slide is a special rule and has its own name, which is the Pascal's rule. It states that n over k is equal to n minus 1 over k minus 1 plus n minus 1 over k. Here you can already see that there's some kind of relation between binomial coefficients, and that somehow with previous binomial coefficients, so for n minus 1, you can calculate the binomial coefficient for n. And this is actually quite interesting, this relation, so let us take a closer look at this now. What you can see here is the Pascal's triangle. It shows us the results of the binomial coefficients of the form n over k. The row here is n, with n equals 0 in the first row, and then increasing if we go downwards. The column is then k, and by column I refer more to the position within one row. So in each row we start with k equals 0 on the left side, and increase k by 1 if we move one position to the right. Now let us take a look at the results. Here you can see the results of the binomial coefficient. This looks quite interesting, and there seems to be some pattern. Again, you can see, as it was stated by the rules already, that n over 0 is 1 for any number n, as well as that n over n is always 1. And additionally, rule 3 and 4 from slide 7 are also present here. N over 1 is always n, as well as n over n minus 1 is also always n. This means that for each row, let us say for example row 6, so the one that has n equals 5, the result for 5 over 1 will be 1, as well as for 5 over 5 minus 1, which is 5 over 4, it will also be 5. Now let us consider the rule number 5 again. I am referring to the Pascal's rule here. As you maybe remember, it stated that n over k is the same as n minus 1 over k minus 1 plus n minus 1 over k. In practice, this means the following. For any position n over k in this triangle, the value can be calculated by addition of the two values that are standing above it. This is, for example, why we have a 6 standing in the middle of the triangle here. 3 plus 3, so the two numbers above have the 6 if you add them up. So this whole triangle is of course infinitely long, and you could add infinitely many rows to it. Now we are already prepared with all the background information and definitions that we needed. We are ready to dive into the binomial theorem now. The binomial theorem states that for any real numbers x and y and any natural number n, the following equation holds. X plus y to the power of n equals the sum from k equals 0 to n of n over k times x to the power of n minus k times y to the power of k. Wow, this looks complicated. But it is actually the solution to what we saw in the beginning of this video. This formula describes the pattern we were looking for. Let us take a look at some examples. You probably remember the first one here. X plus y to the power of 2 equals x squared plus 2xy plus y squared. Now let us reconstruct the solution with the help of the binomial theorem. n would be 2 in our case, because we have x plus y to the power of 2. So the first element of our sum would be 2 over 0 times x to the power of 2 minus 0 times y to the power of 0. 2 over 0 is 1. X to the power of 2 minus 0 is x squared, and y to the power of 0 is 1. Therefore, the first element of our sum will be a squared. Now onto the second one. We would increase k to 1 now. This leads to 2 over 1, which is 2, times x to the power of 2 minus 1, which is x, times y to the power of 1, which is y. So the second term of our sum would be 2ab. Now for the last element of the sum, we would increase k by 1 again, so we would have k equals 2 now. Therefore, the last element is 2 over 2, which is 1, times x to the power of 2 minus 2, which is x to the power of 0, which is 1, times y to the power of 2. And therefore, the last element of the sum would be y squared. And surprisingly, this is exactly what we wanted to end up with. Now for x plus y to the power of 3, it works the same. To practice and understand this a bit more, you can pause the video now and calculate all elements of the sum using the formula of the binomial theorem. The result that you want to get is x to the power of 3 plus 3x squared y plus 3xy squared plus y to the power of 3. Because this theorem is so cool and important, we will prove it now. As stated in the beginning of this video, you do not have to know this proof by heart for the exam, but I nevertheless suggest that you try to understand it, as it is a really good practice for doing proofs by induction, and also because it is simply a very nice proof. Alright, with that being said, let's start. Our goal is now to prove the binomial theorem. If you do not know the formula by heart already, don't worry, it is written in the red box on top here. Now, to prove it, we will perform a proof by induction, so let the fun begin. First of all, we start with the basis step. In this case, it means we set n equals 0, because in our definition of the theorem, it states that n is element of the natural numbers, and the first natural number is 0. And what we do in the basis step now is that we replace each n in our formula by a 0 and check whether the equation still holds. And in our case, this means x plus y to the power of 0, which is 1. And on the other side, if we replace all the n's by 0, we will also get 1. And this means we are already done with the basis step and can continue with the next step now. The next step is the hypothesis step. If you remember, it means that we have to formulate our hypothesis, which is in our case that the formula, if it holds for n, also should hold for n plus 1. I won't read all of it out now because it is such a long formula, but all you have to do here is to replace all the n's with n plus 1 and state that you want this to hold. Now we can move on to the inductive step. This is where all the magic happens. So the inductive step means that we now want to show that the formula also holds for n plus 1. So we want to replace every n by a n plus 1 in our formula and then show somehow with using the hypothesis that the relation holds if we move on from the left side to the right side. In the inductive step, we always start writing from one side. So in our case, we use the left side of our equation that we want to prove, which is x plus y to the power of n plus 1. With the help of the exponential laws, we can easily rewrite this, because we can simply take out one of the elements, because we multiply n plus 1 times x plus y. So it's the same as x plus y times x plus y to the power of n. And you can already see that this is marked in blue here, because it is precisely what our theorem stated. And by stated, I mean that the binomial theorem stated that x plus y to the power of n is equal to the sum of k equals 0 to n of n over k times x to the power of n minus k times y to the power of k. So we can simply use this equation now, which we stated in our hypothesis. So in this step, we use our hypothesis now and replace the blue part by the red part. What we do next is using the distributive properties and take this apart. So we have x plus y in brackets times this sum, and therefore we can take this apart. So we have x times the sum plus y times the sum. Next up, we will move the x and y, which are in front of our sums in the last step, now inside of the sums. And what happens now is that we multiply it together with the x's that are, or y's that are already inside, which is why we will get one exponent more. And this is marked in pink here. So you have a plus 1 in the one sum for the x and a plus 1 in the one sum for the y. Next up, we will perform an index shift. And what we do here is that for the right sum, we will shift everything 1 up. So we start the sum at k equals 1 here. And then we also have to increase the end by 1, because we want the sum to be exactly the same as before, so the elements should be the same. And if we increase the k by 1, we also have therefore to increase the ending by 1. And this consequently means that inside of our sum, we need to lower all k's by 1. Because before k started at 0, and now k starts at 1. But if we want it to be the same terms, we need to use k minus 1 now. Because if it now starts at 1 and you place in 1 for k now, you would still have 1 minus 1, which is 0, as it was before. And all the changes are marked in orange here. What we do next up is that we will remove some elements. So we will remove one element from the left sum and one from the right sum. We do this because we will want the sums to look the same again. And therefore we want them to both start at k equals 1 and run until n. And therefore from the left sum we will need to take out the first element, which had k equals 0. And so if you place a 0 for k, you will get x to the power of n plus 1 from the left sum. This is why this element was taken out and is standing in front now in the darker green tone. And in the lighter green tone, you see y to the power of n plus 1. So here we remove the last element from the sum. And this means that we once replace n plus 1 inside for all the k's, and the result will be y to the power of n plus 1, which is why this is the element that was taken out. So what you can see here is the exact same result that we had on the last line, just that now I already marked that you can see that the sums are now the same. And this is what we need for our next step. So because both of the sums start at k equals 1 now and run until n, we can take them together. So we use everything that is written inside of the both sums and place it inside of the same sum and add it together, which is why it is in brackets here. And the other two elements, which were not inside of the sums, are now standing in front. So this is the x to the power of n plus 1 plus y to the power of n plus 1. And then behind we have the sum and both of the things that were written inside of the sums before. Next up, we will use the distributive properties again. You can see from the previous line that inside of our sum, we had for both sides x to the power of n minus k plus 1 times y to the power of k, just that the binomial coefficient standing in front of it was different. So therefore, we place this in the blue part now, the two binomial coefficients, and take them together inside of the brackets and multiply them with the term behind because they both had the exact same before there. And what we do now is that we will use the Pascal's law. And you have seen this some slides ago. It states that if we have n over k plus n over k minus 1, this will result in n plus 1 over k. And therefore this is marked in green here, and we could simply add them both together, which makes all of it a lot easier now. And now you might see that this already looks quite good. So we have the sum on the right side, and inside of the sum, everything that is written there is exactly as we want it to look in our proof. So this is actually what we want to get, just that we want the sum to start at k equals 0 and end at n plus 1. But besides that, everything already looks perfect. So there is just one more trick that we need to do. And this trick is that we want the elements that are standing in front, which was x to the power of n plus 1 and y to the power of n plus 1, we want them to move inside of the sum again, and we want this to somehow change the limits of our sum. So we want it to start at k equals 0 and to run until n plus 1. And this looks a bit complicated, but let us take this apart now. So we can rewrite x to the power of n plus 1 as n plus 1 over 0, because this is 1, times x to the power of n plus 1 minus 0 times y to the power of 0. And this term is exactly the same as before, just that it's written in a bit more complicated way, but the result is still the same. It is still x to the power of n plus 1. And for y to the power of n plus 1, we do the same. We rewrite this as n plus 1 over n plus 1 times x to the power of n plus 1 minus n plus 1 in brackets times y to the power of n plus 1. And this is still exactly the same as y to the power of n plus 1, which it was before, just that it's written in a different way. And by now you should already see that this looks quite a lot like the sum that we have behind, and that these elements somehow can go inside of our sum now. So if you look at the blue and red elements in detail, they look exactly as the parts of the sum. And what you can see is that for the blue part, everything is the same, and for k we have the 0. So if we take this element inside of our sum, we can set k equals 0. And for the red part, it is the same as if we would have k equals n plus 1. And therefore, if we move it outside of our sum, it ends at n plus 1. And this already looks perfect. So we included the two elements inside of the sum, and this is actually where we wanted to end up with. Yay! And this means we are finally done. We just showed in the inductive step that x plus y to the power of n plus 1 is equal to the sum of k equals 0 until n plus 1 of n plus 1 over k times x to the power of n plus 1 minus k times y to the power of k. And this means we just proved the binomial theorem. Yay! And this is already it for this video about the binomial theorem. By now you should be familiar with factorials, the binomial coefficient, and the Pascal's triangle. And of course, you should also be able to understand and explain the binomial theorem now, including the meaning of all terms and variables that are inside the sum. I hope that you were also able to follow my proof and all the different steps, even though I have to admit that this was not the easiest proof. And that's it for now. I hope you liked this one, and see you again next time.